Okay, hopefully that'll work. So this is the second in our series 2 webinars, and if you missed the first one, it is recorded and available on the website. And if you are registered for this one, you will automatically be registered to attend the one on July 9th as well. So please join us for that. This webinar is being recorded and will remain available for at least a year. Please ask questions as they come up, which you can do by typing in the chat box that you see on your screen. Chris and I will do our best to try to address those. If you're watching this as a recording or you have a specific question or something comes up later, you're also welcome to email us directly. Okay, so for those of you who may not be familiar with IPI and might be wondering why we're talking about this, just as a brief introduction, the Image Permanence Institute started in 1985 studying film and photographic materials, and seeing the importance of environmental conditions on their preservation expanded the scope to address this concern for more materials. And we have moved into how to do so in a sustainable way. So your presenters today are myself. My name is Kelly Krish. I'm Preventive Conservation Specialist at IPI, and my background is in art conservation. I make up half of the environmental consulting team here at IPI, with the other half being Chris Cameron, who's joining us today. His background is as a facilities manager with training in HVAC. So when Chris and I work on consulting projects or workshops or webinars like today, we try to represent both sides of the issues, from collections as well as mechanical. Okay, so with that, we'll get into the bulk of today's webinar, starting with this main question, which is how do you set appropriate parameters? And really, when we say this, what our goal is to define what represents acceptable risk and what will cause unacceptable damage. So just as a review, if you've been joining us for previous webinars, this will all sound familiar. If it doesn't, I encourage you to go ahead and check those out. But where we really stand in terms of preservation for materials is cooler temperatures are generally going to increase collection longevity. So the lower the temperature, we're slowing the rates of chemical decay and we're improving the preservation. The thing that matters most with temperature is those sustained levels of high temperatures, because they are going to have the greatest negative effect on preservation. So it matters less if it's fluctuating or the extent of those fluctuations. It's really just that time spent at those high temperatures that we want to try to minimize. In terms of moisture content, if you recall from the webinar last month on fluctuations, generally the main concern with relative humidity is that we keep it within a moderate range. And we defined this as approximately between 30 to 60% relative humidity. There are some exceptions to this depending on what your collection's history is or what its condition is or certain material types. But for a large range of collection materials, this represents the range when there is the least change in moisture content and therefore the least risk of physical change and additional stress and strain on the objects. And again, just like temperature, it is the sustained high relative humidity that is going to account for the most issues with preservation. So again, we want to avoid high levels of relative humidity when we're setting parameters. And again, fluctuations, as we saw last time, really are not as much of an issue as that time spent at higher levels. So these are all things to kind of keep in mind when we start talking about parameters. So this slide, I know it kind of has a lot on it, but hopefully by the end of this, it'll all make sense. But I just want to kind of lay out the outline for today's presentation. And the main thing here is that the parameters, the appropriate parameters for your context are really going to be arrived at by answering these questions. Do you need to change? Can you change? And what is the best way to do so? And we'll walk through each of these steps. But you can see from the side that the end goal of this webinar is not going to be to give you a single set point and say that that'll work for everyone in all instances. What we're really looking for here is an operating philosophy. So we know that general rules can't be applied to every individual item. The broader the statement, either the less helpful it is or the less likely it is to be applicable in every instance. So we're not looking for a prescriptive number, but we want to find what's best for you. And to do that, you need to take an active role, and we need to figure it out for each given context. So hopefully this presentation will help you to do just that. Okay, we're going to start by talking about the role that standards play, because for a lot of people, when they talk about setting appropriate parameters, standards is where they first start. So these can have a number of sources. There are international standards such as ISO. There can be national committees. There's an example here on the slide from AIC and AAM. There can be institutional mandates. For example, the NPS guidelines cited here. The National Archives also has them, as does the Smithsonian. There can also be inherited practice, whether it's something that you learned when you were in school that you're applying now, or it can be simply that the set points within a given collection space have just remained as they were, without any further examination, which is especially critical to look at those and really assess if that's necessary. Sometimes there's loan agreements or human comfort in place that can really make the parameters pretty strict. And so all of these things are going to play a role in what we can ultimately achieve. Also, you want to keep in mind that these standards are going to apply to different types of collections environments. So, for example, the loan agreements might play a big role in determining what your set points are in an exhibit space, whereas in a storage space, you might have greater flexibility and be able to take into account preservation needs over human comfort. In terms of the history of standards, previously they have been very tight. This is where we usually see numbers given that are plus or minus 2 degrees Fahrenheit, plus or minus 2 or 5% relative humidity. And even though these were developed in very specific contexts, for example, the United Kingdom, they were then applied universally. So it was expected that those same environmental standards would be upheld, no matter where you were. For example, in Arizona, there's obviously a much different moisture load, different temperature extremes to deal with, but they are expected to adhere to those same parameters. Now, most of the people who developed the standards originally did not mean for this to happen, and they recognized that there was a lack of research to feel comfortable with broadening their standards, and they encouraged people to apply it to their own context. But unfortunately, once you give a number, that tends to be, that was the takeaway, and so it got applied in a variety of contexts, which was never intended. So now a lot of the parameters a lot of the standards have been rewritten. And so they're now taking into account more of this context-driven mindset and looking at how you can be sustainable within a variety of different environments. And so two examples where you can see this are PAS 198 and ASHRAE 2019, which I encourage you to check out if you're looking into standards. The example at the right is an excerpt from PAS 198, and I don't expect you to necessarily be able to read it, but it's just to show you that, as you can tell, under general storage, they don't give a specific temperature range or a specific relative humidity range. They have these statements, and then there's notes underneath to help guide you towards further refinement. Okay, so what is the appropriate role that standards can play in setting these parameters? So first and foremost, they can still be very good sources of advice for preservation. If you have a specific archival materials, for example, and you need to know what are the best conditions for their preservation, things like the ISO standards can be very helpful to help guide those decisions. But then in a broader way too, because they've now changed their approach and are emphasizing this context, the necessity for taking into account context, we can also look to them as guides for discussion. So by reading through these, we can see how the parameters may shift depending on the specifics of our collection, our building environment, and we can make sure that we're taking into account all these different variables by walking through this process. Benchmarking is a little different than standards, but can be related. So some examples of benchmarking are the preservation index and then a lot of times for energy management. And so this isn't necessarily saying you will meet the specific, temperature relative humidity range, but it is comparing you to either an ideal from a preservation or energy standpoint, or comparing you to other institutions. So for example, for the preservation index, we don't have any rules saying that you should have a PI of 100 or greater for a storage environment. What we do encourage people to do is to say, okay, if you're starting out from a 40, and we understand that you have a lot of organic materials that would benefit from lower temperatures. If we lower these temperatures, how can we improve the preservation environment? And we can see that if we go from a 40 to 80, we're doubling the lifespan of those materials. For energy management, you might be able to use this to compare your institution to other similar institutions, and if you find that you're spending far more on energy than similar institutions, it can really demonstrate that there might be an issue going on there and make the case for looking further into it. So some good uses for this are to show what your needs are. Do you need to look at reducing energy? Do you need to look at improving preservation overall? It provides a goal to work towards, and it allows you to quantify those results afterwards. So you can say, we have doubled the lifespan, or we are now in the bottom third for energy usage of similar institutions. So these can be really powerful tools for demonstrating how your work has improved the collection and the institution's health as a whole. So at this point, in terms of setting your appropriate parameters, this is meant to say that you want to have identified the needs for the preservation from a risk assessment, as well as from any constraints that would be placed on it due to the type of environment, whether it's a storage space or an exhibit space, or standards such as loan agreements, because these are going to further narrow their parameters.
So now that we've covered this, we have a question. What is possible in this context? What is the best quality preservation environment we can create based on this information? And a lot of this, it involves examination of space and data, rather than just assume I have this type of mechanical system that can achieve this and this type of collection. It involves a lot more in-depth analysis. So some different determining factors in creating a collection space, quality preservation environment, your mechanical system limitations, types of balancing, what your mechanical system is capable of producing, different zones within the system, occupancy of the system. Human occupancy plays a major factor in collection spaces, in determining the environment in a collection space. If you have an unoccupied collection space, you can use different temperatures, cooler temperatures, than you can with an occupied collection space. And we'll cover that in a little bit. The building or room envelope plays a factor. Limited space, preventing your box and box. You just don't have the ability to create a room inside a room factor, and you wind up having a collection space on an outside wall. Costs and access, determining how often you access the material to take them out of storage. Well, let's start at the broad picture. This is what I like to call the onion factor. We have different layers that are going to be a major determination in creating that environment. Beginning with your local climate, your building envelope, your mechanical system, room, and enclosures. Each layer of that onion is going to play a major role in what you can produce. Your local climate, we'll cover that in a second. That's going to be your outside air, your surrounding air outside your building. Your building envelope, how well the envelope for your facility is constructed, how much insulation you have, types of vapor barrier. That's going to determine how well the space is, your building is capable of holding the condition inside of it. Then you get into the mechanical system, the actual systems within your facility that are going to create that environment. How well can that system perform? How well designed that system was. Your rooms, the layout of the room, it plays a factor, the location of the room, airflow inside the room. They're all multiple factors. And then we come down to enclosures. If we're in, we get down to a gallery space or collection storage space, are the collections in cabinets or some kind of storage. And then there are some also lower levels underneath these, but we'll get into those here. But these are the five main layers to this onion. Starting first with the local building envelope, or your local environment, I'm sorry. So we have the local environment, and granted from this map, you can see that every location has pretty much a different environment. We're not going to be the same. Use the United States as an example. There's, I believe, 9 different environments just within the United States alone. So we can't just assume that if I'm coming from New York and I move to, Florida, I can assume certain factors. We want to assess what happens outside of the facility and get that real, analyze yearly trends so we could see certain times of the year we might get heavy rains or we might get really dry, or really assess what happens in that outside environment so we can begin to plan for things in the future and be ready for them for the mechanical system. We drive home the thought a lot here that whatever happens outside eventually becomes your inside air. And that it's very true. Even if your mechanical system, every mechanical system uses some amount of outside air. If your mechanical system is using 5% or 10%, it still has some effect in your collection space. If it's really dry outside, you'll have dry periods. You'll notice your dew point goes down inside your collection space. If you have really heavy rains, you may notice that your dew point may go up in your collection space, even if you're using a small amount of outside air in your system. So comparing those the outside versus desired conditions, here I give one example. So we're looking at temperature on the left and dew point on the right. And our temperatures, our goal is to hold this steady line here. And, well, we're not doing so much outside. We're, outside it's going to go up and down. We have Rochester, New York. Those of you who aren't familiar with Rochester, it gets a wee bit cold out here in the wintertime. So our temperature fluctuates greatly. 2 months ago, we were down in the 30s, and now we were at 90 degrees yesterday, to give you an example. So we get great fluctuations here. So if we're trying to hold this 68-degree line, if we're using a lot of outside air, this is the amount of work that we would need to perform to achieve that. So as we have on the screen, anywhere above this 68-degree line, if we're above that, we have to cool that air that we bring in. If we're below that, we have to heat that air as it comes in. So now we go to the other side. If we look at the dew point, we are trying to hold that solid dew point line. I believe it's about a 45-degree dew point. In the wintertime, anything below this line in our collection space, we are going to have to humidify. Because we're bringing in that outside air, it's drier than the collection space that we're in. So anything below this line requires us to humidify the air. And then as we get into the summertime, anything above this line falls in the dehumidification range. So if you see the shaded parts, both for heating, for cooling, for humidification, dehumidification, to look at that gives you an idea of the amount of work, if we were using almost straight outside air, how much effort we would have to do to make that air usable for a collection space. There's very few places that use 100% outside air, but we will use, again, maybe 5, 10, 20%. And in those scenarios, that's what would be required for the collection spaces. So kind of driving this point home a bit, looking at relative humidity. If you're aiming for, our goal, we recommend to a lot of people staying in that 30 to 60% range. So here we have the outside air for Washington, D.C., up for a full year. So you can see its range, its ups and downs. If we were bringing in that outside air, then you can assume, again, we have to dehumidify here and humidify here. But it also kind of want to make a few points to this. So even at 30 to 60%, it still requires a little bit of work. We still do have to dehumidify probably about 60% of the time, or 50% of the time. We have to add a little humidification about 10% of the time. So we're still, even in this range that we would recommend, we're still doing work about 60% of the year. For those of you who are looking for a really tight window, say you're looking to hold a 45 to, say, 50 range, 45 would be about here and 50 to be about here, that would mean that only 10% of the year are you within range. The other 90% of the year, you're going to be having to dehumidify or humidify that air significantly to make that air usable. So want to give this as perspective to the amount of work that would be needed just to hold a tight condition as opposed to a broader 30 to 60% range. So one of the tools we recommend for assessing data is eCom and notebook software. We want to talk about tools in this webinar a bit. Those of you who are aware, IPI has web-based tool for environmental data management. It is eClimate Notebook. There are a number of proprietary softwares. Whatever loggers you buy will have their own software with them. A lot of them are designed for collection institutions. ePrivate Notebook was, so it helps you do a really good analysis of the risks that your collection face, evaluate the preservation metrics that are built into it, get some reporting, and really get a good picture of what your environment looks like, where your collection lives, and how things are actually being treated. To really let you assess if I'm making changes, are they positive or negative for the collection? And you could bring up multiple data points together and say, okay, I have a photography collection in this space. Are there other spaces that I have in my collection facility that may be better for that collection material? So your building use is going to play a major factor, and this is the next layer down in that onion. Understanding what your building was, the history of your building, is very important. Some of you may have a brand new facility. It was built purposely for a library, for a museum, and that's great. Many institutions don't have that. They're using older facilities. The list below is a realistic list of facilities we've seen. Again, roller skating rinks, janitor's closets, offices, cisterns, rifle ranges. These are facilities that have been repurposed into a collection space of some sort. And with each one of those comes factors or issues to consider or remember. It's important to know what those were because those may echo down as you move on as you go on in that facility. I'll use two examples, one being the car dealership. If you have a car dealership, say they're going to turn it into a museum, a lot of times, from our experience, financially, as they're changing facilities over, they do some cost-cutting measures, and they don't change the facility of their air handling equipment out as they should, or even the building envelope. So you'll wind up with a car dealership, which was meant for human comfort, that is now storing collections, but they never changed the envelope or the facility or its ability to handle the collections. So what was only ever meant for human comfort can still only really sufficiently supply human comfort without taxing the equipment, or the equipment can't achieve it anyway, or if the equipment can achieve it, maybe, excuse me, the envelope can't hold that condition. The similar can be said using the cistern as an example. The cistern was meant to hold water. And in some two circumstances we've seen now, a cistern has been repurposed to hold collection storage. The problem being you have a space designed to hold moisture, designed to hold water, and the collection materials in there being stored generally in a basement as the cisterns were, the moisture level is already high. And as that humidity builds up, it isn't able to escape from the space, and they wind up having mold issues within that space because they're putting collections in a space designed to hold moisture. So it's really important to know that history, what the building was used for, because it helps you evaluate what you may face and some of the troubles that may come at you. Another thing we recommend is understanding your building use. Walking through your facility, making a map of spaces. This is the image you see here on the right is just a floor plan that was taken, emergency evacuation plan that was used to lay out where all the collection materials were in a space. And it's used mainly to understand the arrangement, the distribution of spaces, not just for your collection, getting an idea for where the offices lie, where your public spaces are, where your staff spaces are. We have come into situations where the director's office was located adjacent to a collection space. Mapping that out, if you walk through the building, it wasn't truly the building was kind of a maze, so you didn't understand what backed up to which rooms. As we laid it out, you see the director backs up to the collection space, and they were actually served by the same air handling unit. So when collections would call because it was getting too cold or too warm in the space and they wanted it cooled off, the director would call and want the temperature turned up. And at the end of the day, who wins that argument is going to be the director. So just getting that understanding for how your buildings are laid out, where the air is distributed. And understanding your building and room envelopes as well. There are what we call heat loads and sources of moisture. If your collection space is on an exterior wall, you're going to have some solar gain potentially through the wall if there's insufficient insulation. That's the transmission through the exterior, infiltration from surrounding spaces. If you're trying to run a 50-degree vault that's poorly insulated inside a building that's surrounded by hallways that are treated to 72 degrees, the hallways are going to act as a heat upon the space. Similarly, there's other issues. Construction materials, the presence of insulation, vapor barrier. If a room has poor insulation or poor vapor barrier, that's going to cause significant inabilities to hold temperature in a space. Lighting within a space, if we use our past experience, lights have caused heat loads of anywhere from 3 to 5 degrees in some serious circumstances, but 3 to 5 degrees in some collection spaces. So the lights within a space can play a significant factor. And I skipped windows on purpose. I'll cut back to that really fast. Windows and openings, holes in walls, old pipes, or even where the ductwork used to go can cause issues in space. But windows we see usually being a major factor. As an example, we have 3 data loggers here on the screen you can see, and they're all on the same floor on a library space in a city, northern city, east-facing windows. And you see these spikes every day were occurring from 8 to 12 o'clock. And it's solely from the sun shining in the window and heating up that one row of where the collection materials were. So for about 4 hours a day, we were making book jerky in this one row of books. You can see same is not felt on the backs, the stairwell, the main stairwell. They just kind of move along. And at some points, the temperature reached over 110 degrees. The really disturbing thing in some respects is if I say it's a northern city, this was occurring during February. So we're seeing 110 degrees in the coldest time of year on the east-facing window. So what could happen during some of those summer seasons? So it's something to keep in mind. In this scenario, we recommend to look at boarding up the windows, covering them, and you can actually see that begins to happen around here and it starts to even off. So your mechanical system, the next layer down on that onion as I'm describing, this is your system that's going to be what provides your heating, your cooling, your humidification, dehumidification of your air as it passes through, whether you're using 100% outside air or recirculated air. These systems are going to determine what happens, what's allowable, what type of environment you can actually create from the air you're bringing in and the spaces you have. So understanding your mechanical system is very important. One of the critical things to know about your mechanical system is the dew point that your system is capable of producing. Getting to know what dew point you have allows you to put that, if you can get that information, put that into dew point calculator, which we have a link to down here. It's a free website. Back up. dpcalc.org, and you can plug that in here into the dew point side of the graph, and then using that you can go and plug in your relative humidity and temperature. I'll cover some of that in a few minutes to get an idea of what your collection space is capable of producing. All right. So some typical issues we see with mechanical systems, the dew point off of the unit. And when we say dew point off, it doesn't mean that it's turned off. It means that a mechanical system was designed initially to produce a dew point of, say, 25 or 45 degrees or even 40 degrees. And over time, that dew point has actually crept up, and it's gone from 45 to 50. And in that gain of 5 degrees or loss of 5 degrees, it reduces the system's ability to cool the space, to dehumidify the space, and causes a collection environment to lessen the quality over time. Also, some poorly functioning equipment, reheats being left on too long, humidifiers working or not working properly, lack of control. The building management system is drastically important. I'll cover that in just a second. But the building management system is going to determine what you can do for your collection space without having to manually make changes, and having that ability is huge, or even no humidification abilities whatsoever, especially in dry climates, can be quite an issue. So building management system was what I just briefly talked about. This will be, not all facilities will have this. Some Some facilities still are in manual or have pneumatic systems that will control them, but the building management system is software that will allow you to really control your mechanical system, to put in set points, to shut things down, change fan speeds, check operations. It really allows you a full control of your mechanical system to make any changes, adjustments, and assessments that you can. Some other determining factors when you're evaluating your collection or your mechanical system and your set points. Salts in the air can be a major factor. In speaking with an engineer recently, he had told me that salts can be felt up to 50 miles inland from a major salt source. So say an ocean. So if you're within 50 miles of an ocean, there's potential that the air in your collection space could still feel effects of the ocean, even though you're over an hour away from it. Dust storms, wildfires, if you have inefficient filtering, those can play another factor as you'll have effects of that within your collection space. Campus policies, if you're on a university campus and they shut the chilled water down on you at certain points of the year will be a factor. And even remoteness. There are facilities out there that their maintenance team can be over 2 to 3 hours away, and just if you have a problem at 2 in the afternoon, that means you're not having that problem fixed till the next day. So it's just another deciding factor. So let's look at setting those set points or creating those set points. If we go through here, we're looking at creating a summer set point for a collection space. What we want to do, to set a summer set point, we want to enter using dew point calculator. We want to assess what we can do. So we would use whatever we determine as the achievable dew point, whether that's from discussing that with your facility staff or determining that from data. Whatever we determine is the dew point we can achieve in the summertime, and it doesn't have to be even summertime. Hot, humid conditions. If you're in a hot, humid environment, you maybe see summer-like conditions year-round. But we want to take what we know the dew point system can achieve, and we want to enter it in the far dew point column on the right. From there, we want to consider the highest limit of relative humidity we can recommend, our collection can accept, which is anywhere from 30. We recommend 30 to 60% relative humidity. I put in here 55 just to be on the safe side, give us some wiggle room. A lot of times mechanical systems will give you a 5% range. So if you ask for 55, you'll go from 50 to 60 in swings over time. So we put 55 in here, and if we put that 55 in, dew point calculator will tell us the lowest possible temperature that we can achieve with that current design of that system. So let's look at winter, similar for doing a winter set point. Almost a similar scenario for determining winter or cool or dry scenario set points. One of the things we do is we look at our outside air again. We want to determine, looking at the outside air, what's the average dew point that we would see in the wintertime. And here I used Rochester as an example. In the wintertime, our average dew point is 32 degrees. So in that dry condition, we put that 32 in. And then using that 30 to 60% relative humidity range that's acceptable, I put the lower limit in there because we now are in a drier condition. Putting that lower condition on there, we can then see the coolest temperature that we can achieve, or the safest temperature that we can achieve within that range as well. So now getting down to one of the lower layers of that onion, the room for the room the collection lives in. So if you look on the right of this image, we have a pretty standard collection space. We're storing paper and compact shelving. Everything would be great. We can use, if you just look at the right side of this image, we could use cool temperatures. This is in a subgrade collection space, surrounded entirely by other collection spaces. So we could, in theory, use cool temperatures all day long, all year long, to help improve the longevity of the collection. However, now if you look at the left side of the image, we see a desk and a staff person in there. As soon as we have the presence of staff or a desk or working space in there, we have to account for human occupancy in there. And accounting for the human occupancy now means that we have to make human comfort a factor, which we can't do cool temperatures. As long as that person is working in that space, we'd have to use 60, coolest I would say would be about 65, but typically 68 to 72 degrees. Removing a staff member from a collection space, having the collection space dedicated to collections is very important to being able to provide a cooler environment. So getting a little bit further down there, storage, housing, and furniture. The better you can collect your, the better you can protect your collections. Is going to allow better buffering capacity. Vitrines, compact shelving boxes, they all allow for a better buffering capability for the collections, better to prevent their exposure to swings that we may feel from outside elements or outside forces. So that gives you that added effect. If you have a collection space that you know, even though you have a good mechanical system envelope, still experiences some really drastic swings, trying to buffer the collection as much as possible would be very important to helping out, helping protect them from those swings.
Okay, so we wanted to address as well the role a historic building would play. Many institutions don't have a purpose-built structure or aren't looking to build one brand new, so they're often in historic buildings, and a lot of times this is even considered part of the collection. It's an important part of the institution, and so we want to be sure not to damage it in any way. So this is just going back to the standards, for example. The importance of the building was emphasized through the New Orleans Charter, which really talked about how the building itself is an object and has specific needs as well and should not be sacrificed to create a certain environment for the collections within them. So just wanted to show a few examples of this. These are some historic structures, and because they don't have insulation or vapor barriers within their walls or between them and neighboring structures, the fact that there were different conditions in the structures next to them, it drove moisture through the walls. And you can see that this is causing damage to the objects as well as the building itself. In the image on the left, you can see that there's some waviness or cockling to the drawings that are hanging on the wall. You can also see, if you look closely, that there's some brick dust that has kind of accumulated, and so you can see how the brick is starting to deteriorate as that moisture is moving from one source of moisture to a source of lower moisture. And then in the image on the right, again, there was a different level of humidity in the structure next to this one, and so we start to see this peeling paint. So the issues we run into without having a vapor barrier essentially is because we're creating a moisture gradient. We're creating a difference between what's outside the structure and inside the structure, and that's causing the moisture to move from one area to the next. And so it's going to move in the direction of the lower humidity and try to reach that equilibrium. So this results in damage to the structure as the water pulls components from from the building envelope. We can see this in the form of efflorescence on bricks. If you've ever seen it, it's like almost like a white salt that you'll see on it. Condensation can form within the walls, which allows for the corrosion of interior structural and piping elements, as well as the potential for mold germination. And there's a loss of efficiency, as the mechanical system must continually compensate for the load or the loss that's coming from outside. So this is important when you're considering your parameters, because the greater the difference between the interior and the exterior environment, the greater the issue is going to be. So you really need to work closely with your architect or the rest of your project team when you're setting these parameters to make sure that you're not driving moisture through the building itself. One source that you may want to consider is the ASHRAE 2019, Chapter 24, and within it, it does have a table that lays out the type of building envelope necessary depending on your climate zone and what type of control you're trying to achieve. So this kind of this is a helpful way to see how all these parameters interact. And I'll also say that taking the building into account and setting these standards, you can see again my point from the beginning about how they've tried to make it more context specific is that there are different levels of control. So the levels of control that are set for purpose-built structures are different than those that are set for those who need to reduce stress on their building. So, so we can take those into account and look at the recommendations for how we might need to consider our parameters with regards to our building envelope. Okay, the final section is just what is ideal in the specific context. How do we take what's practical and what our goals are, and how do we implement it in the best way possible? Again, a reminder is that our optimal storage environment is one that achieves the best preservation of the collections with the least possible consumption of energy. So I'm just going to give some basic recommendations, and then we'll go into an example afterwards. So first, start with the big picture. When you're setting parameters, you want to first focus on reducing extremes. So depending on what your capabilities are, this might be as far as you can go. But we know that that's the most critical for improving preservation. It's trying to keep the extreme levels of temperature and relative humidity levels that might go above 60. What can we do to reduce those to set safe parameters for our collections? I also would recommend that you start with a broad range and then handle specific objects or specific collections with as microclimates. So we don't want to manage the collection as a whole based on the object of greatest need. We want to find the greatest common denominator, and then we want to treat those objects that need additional considerations with focused efforts that can really, we can maintain those environments to more specific standards. Also want to prioritize and plan. So not all materials are going to benefit from certain conditions to the same extent. If you have a room that has maintained levels of lower temperatures, the ceramics and the glass, your inorganics really aren't going to benefit as much for the most part as your organic materials might. So we want to make sure that, and I think in the example here, if you have a cold storage facility, you don't necessarily need to convert your entire storage space into a cold storage area. You can just build a cold storage that has the proper footprint for those materials that need it. Also would recommend that you locate those materials strategically. So if some rooms might have lower temperatures, some rooms might have better humidity control. So you can fit the needs to the parameters by locating the materials within different rooms, and also making sure to avoid any harmful microclimates. If you have areas that tend to have higher relative humidities, try to put objects that would be less affected by those in those spaces, or more ideally, don't use them for collection spaces. Additionally, if you are looking specifically at cold storage, we often recommend that institutions kind of pull together for their resources rather than have, say, 6 different cold storage spaces across a city. If you have one localized space, it's a lot easier to maintain those conditions, and it's much more efficient. And as Chris had mentioned earlier, we definitely want to manage people. So if we separate collections and occupancy, we're better able to meet the goals for both, and we can set more appropriate parameters for each of their needs. Also, again, as Chris mentioned, we want to be sure to address issues of load. If we can remove sources of temperature and sources of moisture, that will allow us to better meet our parameters that we'd like to set. From there, from addressing the issues, we want to make sure that we're maximizing the use of non-mechanical methods. So that means, we want to allow for air mixing. We don't want to block vents. We want to allow for the natural ventilation, reduce the chance for microclimates, so that the parameters we set are really what's being felt for all those objects within the space. And again, with insulation and vapor barriers, we can maintain those parameters in more efficient ways because we're not losing those conditions to surrounding spaces or to the outside. And also, you want to keep in mind the mechanical systems aren't meant to provide conditions that are totally at odds with what might be in your local climate. The intention is for them to trim extremes. So one example we wanted to give of how to operate mechanical systems strategically is the seasonal set points. And the link there will take you to our methodology, and you can download to the section on seasonal set points to learn more about the benefits of doing so and how you might implement it in your own institution. But I wanted to illustrate some data here from one location, and on the left is temperature and on the right is relative humidity. And you can see that when we talk about seasonal set points, we're not talking about letting the temperature, skyrocket up or the relative humidity go out of control. We're talking about, reasonable changes from one season to the next that allow us to maximize preservation and sustainability. So, for example, with the temperature, in the winter, we're maintaining about a 55-degree temperature, and then in the summer, we allow that to go up to a 65-degree set point. So we're in the winter, we're definitely getting some more gains. We're slowing down those rates of chemical decay, but we're still preventing the extreme temperatures in the summer. And you can see for relative humidity, that winter set point is around 45, and the summer ends up being around 55. So these work together really well because we know that as we lower temperatures, we're going to increase the relative humidity. So by keeping the temperatures lower in winter, not only are we reducing the amount of work we need to do to heat that air, but we're also keeping the relative humidity within its range. The same goes vice versa for summer. By raising those temperatures, we're keeping that relative humidity a little bit lower than it would be otherwise. And so we're able to meet those preservation goals without having to do additional work to dehumidify the air. So I will say that this example is specific to environments that tend to have distinct seasons, but similar, the idea can be applied to other environments as well, as long as there's some kind of variation across the year in terms of the humidity or temperature levels. Okay, so here's that slide again from the beginning, and hopefully it makes a little bit more sense now. So again, we're going to start by defining our goals and priorities, and we're going to do that by using the risk assessment process to determine what the materials in our collection need. And the standards and benchmarking are going to help to inform this, as well as setting our goals. So we know if we want to preserve the specific material, let's say it's acetate film, then we'll look at the standards and we see that we need cold storage. So we know if we need to lower temperatures, then we're going to need this kind of building envelope for our climate. So that can be a helpful way of outlining what your goals can be. Then we move on to what can you change. And by doing so, we're going to look at the systems, spaces, and data to see when the work will need to be done. We're going to look at the local climate, and we're going to see, first of all, how similar is it to what our needs are, and then how do our set parameters determine when the work will need to be done. We'll also need to determine how much can be done with the mechanical system. One example that Chris showed was through the use of BP calc, and we want to be sure that in the process we're not damaging the building envelope. And in addition to the can you change, you want to be sure to look at the other issues that might need to be addressed in order to implement these changes. So consider what your loads are. Are there any occupancy concerns that you would want to separate in order to be able to change? And then finally, what is the best way to do so? That's going to be, again, by separating out occupancy and collection spaces and allowing you to meet the goals of each individually. Prioritizing objects and handling those that require specific conditions through microclimates rather than through the management of the environment as a whole, and through sustainable operations, such as the example of seasonal set points. So I think that illustrates how, rather than one parameter, we're really looking at different ones depending on what's going on outside and being responsive to the specific context. All right, well, thank you very much. We did want to encourage everyone to please consider taking the time to complete the brief post-webinar survey. I believe there's 9 questions or so, and this is, if you were present for the webinar before this is a different survey. But I did want to say we really do pay attention to your feedback. The information gathered helps us to evaluate our approach in this grant and strengthen our educational resources in the future. So for those of you who gave feedback for the previous webinar, we were you encouraged us to provide some references for further reading, which you'll see now if you download the PowerPoint. Those are there. And you also suggested that one-pagers might be helpful to kind of summarize the content and provide a resource to be able to distribute across your institutions. So that is something we are working on as well. So we definitely do take your feedback into account, and we really appreciate it. Okay, so with that, I think we'll go ahead and start to address some questions here.
We have one question from Megan Smith with COVID advice, including increasing as much airflow between outside and inside. What do you think will be the effects of this over the next year? It's a very good question. We're actually still trying. There's not just us, but there's a number of people trying to determine how that's going to actually relate to collection spaces. We've looked at some data for a few institutions where, depending on your mechanical system, the increase in outside air, the mechanical system may be capable of handling the load that's being placed on it. The increase of outside air, the mechanical system may have been over-designed, and bringing in more outside air, the system can just be using the BMS that we talked about turned up, if you will, and you won't see a change in the effects of the outside air, but you will be using more energy as a compensation. But on the flip side to that, if your mechanical system can't handle it, there is potential, depending on your location and depending on the time of year that this continues into, through warmer periods, more humid periods, if your mechanical system can't handle it, you may see increased temperature or relative humidity. Or if we get into cooler, drier seasons, periods, you may see lower temperature or lower relative humidity in your space, because that outside air is going to start to play a factor. And again, we talked to someone this morning that said, when I noticed during major storms come through, major thunderstorms, I'm seeing spikes, and it'll be maybe unfortunate, but maybe what we have to live with as a, I guess, would you say, side effect of the current situation we're in. ASHRAE, we understand exactly why ASHRAE implements them. They're very good rules, recommendations to follow, so we kind of have to live with them, unfortunately, at this point in time.
Yeah, and I think, I believe the ASHRAE guidelines also still recommend that you keep the relative humidity between 40 to 60%. So whether that is achievable or at odds with the outside air intake is definitely going to be dependent on the context. So it's something that is evolving, and we're learning more about it, and hopefully we'll have some more answers about how that can affect collection spaces within a few months. So
we have another question. How are dew points established for mechanical systems? It's kind of a tricky question, but you normally, at the design of a mechanical system, the ME, mechanical engineers on the project, will, based on whether it's the chilled water temperature or if they're using refrigerant, whatever supply of refrigerant material they're using or cooling material for the system, they'll design a cooling coil, and whatever it's trying to word my sentence carefully, roughly the temperature of the air leaving the coil can help determine your dew point. If you have a cooling coil that's capable of producing, say, 30 to 40 degree temperatures, and the air passes over it, then we can assume the air leaving that's like 40, 41, 42 degrees. And that if you're passing 50 degree dew point air over it, it'll wring some moisture out, and the leaving dew point should be 40, 41-ish. So it's really based upon the design of the system when they're building it, based off of many underlying factors.
And then the final question we have now is, if you have a dedicated storage room with an adjacent workroom and each is kept at a different temperature, should one be concerned about bringing objects from storage to the workroom for cataloging and then returning it to storage? That's an excellent question. So the main thing that we're concerned about in that instance is condensation. And condensation is only a risk when you're moving from a colder area into a warmer area, because as you know from having like a cold glass outside, the condensation occurs on the colder surface. So we're most concerned when we're taking a cold object into a warmer environment. So in order to avoid condensation on the object, there are a couple of different approaches. The first one would be that if the temperature of the object needs to be above the dew point of the space. So if you have that information, you can determine if condensation is a risk. If it is, depending on how different your temperatures are, then you would probably want to consider something like bagging the object and allowing it to equilibrate to the temperature in the new space before removing it from the bag. Another approach that people will sometimes use is having kind of a space in between the two that the object can kind of transition through. So again, that question, the answer depends on what the specific set points are, but the main concern is to avoid condensation by always making sure that your object's temperature is above the dew point of the space you're moving it into.
Next, you have a recommendation.
Okay, so there's a question about recommendations for creating a microclimate in which the relative humidity is higher than the relative humidity in the rest of the room. Paper and wood, and then that's a good question. We don't usually see wanting to create a higher relative humidity. Usually, it's a great question because usually microclimates are used to reduce humidity, in which case we use sorbents and other materials. I'm not sure I have a very good answer for you right now. I think that it might be possible to still use some sorbents, and if you create a sealed enough case, you should be able to maintain conditions. But I think that's a question that I would really like to run by some others in our office and maybe get back to you through email or some other way. That's a good question.
And we have another question. Is there a source that explains the influence of surrounding natural elements on a building, trees, vegetation on the ground, type of ground? There are a number of sources out there. Unfortunately, off the top of my head, I wouldn't want to ramble them. I know, I believe Department of Energy or Energy Star has had some in the past that explain ways to either shade your building or avoid moisture near your building because of them. But Catherine, I can look up some of those and email them to you when I locate some of those, because I know that they're available. Just I don't want to cite sources off the top of my head without knowing exactly.
And they definitely play a role. We have seen institutions that have different dew points at different sides of the building, and it has to do with the amount of shade available. So it can definitely play a role. I just wanted to add too, someone shared that there was a talk at AIC about this earlier in the week, and I think that relates to the question about microclimates, so that might be another source to check out as well. Okay, so to better interpret the needs and the climate parameters of an historical building, what are the professional profiles of the personnel who can analyze the conditions? For the most part, a lot of times we work with teams, and they tend to compose. You would definitely want some kind of an architect on board who's familiar with the building materials.
Yeah, if you're doing any assessment on a building envelope in general, I would definitely want to. My recommendation would have an architect look at that to really be able to assess what the materials are and what insulation level they produce, what type of vapor barrier they have, give you a really good, almost, if you will, educated opinion on what the structure is.
And there is some software they can use as well to model that. We'd also would definitely recommend that if you're looking for someone to be able to do that, do consider making sure that they do have experience with historic buildings, because as we mentioned, a lot of the options, we want to be respectful of the building, and so a lot of the options, for example, installing a vapor barrier or something like that, we really wouldn't want to do to a historic structure. So finding an architect who has experience and sensitivities to the needs of the historic structures would also be a critical component in terms of their qualifications. Okay, I don't see any more questions at the moment, and we're just a little bit past time, so I think we're going to go ahead and end the webinar now. But as we mentioned, if you have any further questions, we're happy to address those through email or by phone. Both Chris and my contact information is available on the screen as well as on the ITI website. So thank you all very much for joining us, and we hope to see you all in July for the final webinar.